Hello everyone, this is topic 7 for exam 4, part 3 of topic 5, 6, and 7, and it's called the limit comparison test. So this is used when we cannot establish a direct term-by-term comparison easily, or if the direct comparison test fails. So the nice thing about this theorem is there's no direct comparison to make. All we have to do is we're still going to let the sum of the a sub n be the given series, and the sum of the b sub n be the series we are comparing to, or the comparison series if you like. And we also have to let a sub n and b sub n be greater than 0 for all n. So remember the distinction between these. This is referring to the sum of the series, and when we say this, a sub n is greater than 0 and b sub n is greater than 0 for all n, it's referring to the particular terms in the series. So in any event, the theorem just basically says to take the limit as n goes to infinity of a sub n over b sub n. And if you get some number L, so you have to get a value of L that's finite and positive, then the two series are going to do the same thing. They're either going to both converge or both diverge. Now, the one thing about the limit comparison test that I didn't mention here in the notes, but is evident on this table, so remember our special table, you can see that we've already doctored it up a little bit here, where it mentions the just want to compare these. I've already told you about letter I under the comparison cluster. Letter I and II are for the direct comparison, and letter III is the limit comparison test. And you can see it basically says the same thing. Take the limit of the ratio of a sub n over b sub n if it equals c, which is greater than 0, which is the same as saying it's L, where L is finite and positive. Then both series converge or both diverge. But here's an important thing. In the, they do mention about, as we've talked about, the comparison series is often geometric or P. But this sentence talks about how to find b sub n in the limit comparison test. And that is only to consider the terms of a sub n that have the greatest effect on the magnitude. Okay? And what that is, when we're dealing with a ratio of two polynomials, such as what we have here, okay, we're going to call this the sum of the a sub n, and we're going to have to pick a series that we're going to call the sum of the b sub n. And what you do is you just focus on the leading terms of the polynomial. So in this case, n squared over n to the fifth. You don't even worry about the coefficients. You just take the highest power in the numerator over the highest power in the denominator, and then simplify that ratio to be a p-series. And canceling two factors of n, we get 1 over n cubed. So therefore, we're going to compare this to the sum of the b sub n, which we'll take to be the sum as n goes from 1 to infinity of 1 over n cubed. Okay, so again, to get the comparison series, you don't care about anything except the leading or the highest powers of n in numerator and denominator respectively. You take that ratio, simplify it to get a p-series, and that's what you're going to compare it to. Okay, so then the theorem just says take the limit as n goes to infinity of a sub n over b sub n. And that would be the limit as n goes to infinity in this case of, okay, let me make that a little thicker, fraction bar, because we've got fractions going on both in the numerator and denominator. Numerator is a sub n, 2n squared plus 1, 5n to the fifth, plus n cubed plus 1, and the denominator is the 1 over n cubed. Okay, I would suggest a little bit of algebra here. Rewrite the fraction that's in the numerator. And then multiply by the reciprocal of the fraction in the denominator, so times n cubed over 1. And then even go so far as to distribute that n cubed in the numerator. And if you wanted to put parentheses around these, that's fine. Not really necessary the way I've written it. But now distributing that n cubed in the numerator, we get 2n to the 5th plus n cubed over 5n to the 5th plus n cubed plus 1. Okay, and here's that special type of limit. We haven't used this in a few lectures, but remember this limit. When you have a ratio of two polynomials and the degrees are equal, the limit as n goes to infinity is just going to be the ratio of the leading coefficients. And so therefore, by inspection, this limit is 2/5. Make sure you understand that property. It makes life a lot easier. Okay, and I'm just going to say that it's greater than 0, meaning that it's finite and positive. And now all we need to do is determine what does b sub n do. So now the sum of the b sub n was the sum is n goes from 1 to infinity of 1 over n cubed. You have to tell me what type of series it is. Hopefully you can immediately recognize that as being a p-series with p equaling 3. Look at the table if you need to regarding p-series. When p is greater than 1, it converges. So remember what the theorem said. We'll look back at it in a moment, or look at the one on the table if you like. But it basically said that if you get a limit that's finite and positive, the two series will do the same thing. They'll either both converge or both diverge. So now by the theorem, again, this is a necessary step, the sum of the a sub n, which was this complicated looking series, that this would also converge. Okay, a little line in here to separate these two. Okay, so final example, number 2. We're going to call the given series the sum of the a sub n. Off to the side, I'm going to take the ratio of the highest powers of n in numerator and denominator respectively. So n over n squared. So this again is how we determine our comparison series. Again, as it says on the table, right? The ones that have the greatest effect on the magnitude, and those are always the highest powers. So, when you take the exam, I'm going to be deliberate, and I will tell you the type of test to use. So if you get familiar with this table, because I'm allowing you to bring this into the final exam with you, if you get familiar with this table, then hopefully you're finding things easy, because you just go to the test. You remember, of course, about, make a little note here about the magnitude if you want, and it tells you what to do. Take the limit of the ratio of a sub n over b sub n, and then they both converge or both diverge. So let's make our comparison. So we're going to compare it to, call it the sum of the b sub n sum is n goes from 1 to infinity of 1 over n to the first, or just simply 1 over n. I forgot to do my cancellation over here, but we had n over n squared is the highest powers in numerator and denominator respectively. And remember, you're always reducing this, and it's always going to turn out to be a p-series. So take advantage of that as well. Alright, so now the limit is n goes to infinity of a sub n over b sub n. Is the limit is n goes to infinity. Okay, if you want to make this fraction bar a little thicker. Okay, a sub n was the n plus 1 over 3n squared plus 1. B sub n was just the 1 over n. Do the division. Rewrite the fraction in the numerator. Times the reciprocal of the fraction in the denominator. If you wanted to put parentheses, that's fine. And we're going to suggest at this point that you distribute the n that's in the numerator, so we get n squared plus n over 3n squared plus 1. And take advantage of the fact that these always work out such that you will be able to use that special theorem, where you're going to get a fraction, which is a ratio of two polynomials, where the degrees will be equal, and the limit is just going to be a ratio of the leading coefficients. Slip the little 1 in there, so that limit is 1/3, which is greater than 0. So it shows it's finite and positive. So now consider, what does the sum of the b sub n do? And that was the sum as n goes from 1 to infinity of 1 over n. Okay, this is that special p-series, what we call the harmonic series. Exponent, of course, here is 1. But this is the breaking point for convergence or divergence. Because if you look at the table regarding the p-series, when p is less than or equal to 1, that's when it diverges. So 1 is like the breaking point, if you will. So it's less than or equal to 1. So then we could say it diverges. And then the final statement by the theorem, the sum of the a sub n, which was the sum as n goes from 1 to infinity of n plus 1 over 3n squared plus 1, that this will do the same thing. Or in other words, it diverges as well. Okay, so that's the end of that. Come back when you're ready for topic 8.